Okay, so we are ready to look at example 4. This is on page 89 of the workbook. Okay, and this asks us to do a little bit more work with determinants. In particular, we're looking for patterns, kind of ways that determinants behave if we take a matrix and change it a little bit. Okay, so if we read the instructions together, for each of the following, we're given a matrix and a related matrix B. How are their determinants related? Okay, notice that these matrices are 2 by 2s, so those types of determinants are a little bit easier to calculate. So let's look at part A here. All right, so if we take the determinant of A, by definition, that's just going to be AD minus BC. Okay, and the determinant of B, same idea. Okay, this time though we're going to get CB minus DA. And the question that we're trying to answer is, do we see a relationship between those two calculations that we did? And you might notice that the determinant of B is just the exact negative of what we got in A. Okay, so we could summarize this by saying that the determinant of B is just negative the determinant of A. You might ask yourself, how are A and B related? Okay, well, notice that the rows are just switched. Okay, so to get from A to B, we switched the rows, and so kind of what we've determined here is that switching the rows of that matrix just negated the value of the determinant. That's a fact that turns out to be true even if we had a bigger matrix. Okay, so moving on to part B, similar type of a question here. Okay, in this case, you can maybe see that the relationship between A and B is that we got to B by just taking the first row of A and multiplying it by K. Okay, otherwise the matrices are the same. All right, we're going to do the same thing that we did before by just calculating determinants and see what happens. I'm going to start with the determinant of B in this case. Okay, so by definition, we'd start by taking A times KD and subtract B times KC. And you might notice that we can do some algebra there. There's a K that occurs in both of those terms. We can factor it out. And interestingly, AD minus BC, that's just the determinant of A. So we get a relationship between the two determinants that looks like the determinant of B is K times the determinant of A. Okay, way that we could summarize that is if you take a row of a matrix and multiply it by a constant, you just end up multiplying the determinant of the matrix by that same constant. Okay, and finally, let's scroll up a little bit here. And for C, we're starting with the same matrix A, B, C, D again. And how is the matrix B related to that original matrix? Okay, that's not quite as easy to see, but if you think about it, we can get B from A by just taking K times the first row and multiplying it by the second row. I'm going to write that down in words. Add in other words, you can get B from A by just doing a row operation, okay, of a very common type. Okay, and same question, we'd like to know, is there a relationship between the determinant of these matrices? Okay, let's scroll up here a little bit. Well, let's see what we would get if we took the determinant of B. Okay, so if we do that, just using the 2 by 2 formula, we're going to take the diagonal entries times each other. A times KB plus D minus B times KA plus C. Okay, and this time we need to do a little bit of algebra. Okay, so if we multiply that all through, KAB plus AD minus KAB plus BC, or I'm sorry, minus BC. something interesting happens here. Notice that we get a KAB and a minus KAB. Those two terms cancel, and look at what happens. We just get AD minus BC, which is exactly the determinant of A. So what we've just demonstrated is if you do a row operation, you take a multiple of one row and add it to another, it leaves the determinant of the matrix unchanged. Okay, how can we summarize this discussion? Okay, well, what all of the examples in A, B, and C have in common is that they all represent row operations of some sort. Okay, and so doing row operations have predictable effects on the determinant of a matrix. Okay, and we're going to summarize that in the table here just by making the same observations that we did when we worked through A, B, and C together. Okay, so starting in the first row here, if we take a matrix A and switch either two rows or two columns, okay, if we kind of generalize from the example that we did together, the effect on the determinant is just to multiply it by -1. Okay, that's what happened in part A of the example. Okay, the next one, one row is multiplied by a constant k. That was like example B, and we discovered that the determinant of A gets multiplied by k in that situation. Okay, and then in part C above, we took a constant multiple of one row and added it to another, and we discovered that the determinant didn't change in that situation. That turns out to be true of any square matrix that you want to look at. Okay, so why do we bother with this? Well, basically, we put these three facts together in the right way. We can use it to prove the next theorem at the top of the next page. Okay, this is a corollary to theorem 4.7, which gives us a way of determining the determinant of an inverse of a matrix. Okay, it turns out that it's just 1 over the determinant of the matrix. Okay, I'm not going to go through the proof of this theorem, but if you're interested, you can look at my notes and see a sketch of the proof, and I can tell you that it's going to basically make use of the facts about determinants, okay, that we kind of summarized above. That's the reason why those are